Students, welcome back to the part 2 of lecture number 28. So, we are discussing about the first unsupervised DNN technique, that is the autoencoder, right. And we said that autoencoder is basically a technique which is used to reduce the higher dimension data, or it can be used to find out the hidden features, or it can be used to denoising the data, remove the noise from the data actually. And to be frank, it decompresses the data, or it compresses the data, apply the machine learning model on it, and then decompresses, which is widely used in image processing, right. If you have a large image, you want to apply a machine learning on that. If you want to apply machine learning, it will take a lot of time, or learning will be much more difficult. So, what you do is you compress the data. Once you compress data, you can do this dimensional reduction. Then you apply the machine learning model and do everything, and then decompose the data to find the representation of the input data. That is what is done. So, it has 3 parts: encoder, latent space, and decoder. Let us talk more detail about it. And encoder maps the input data to the encoding or hidden representations. Normally, it uses some kind of weight functions. Okay, encoder does that. So, let us do it. So, encoder will map the input data x to an encoding function which can be also hidden representation. Hidden representation using a set of weights. Weights are very common, and biases. Go back to my slide on the multi-layer perception MLP. So, H, if H is this encoding function H is nothing but a function of what? Weights into x plus bias. That is what it will map this x to an encoding function, and the encoding function is H. Here this F is what? It is an activation function of the encoder. It can be any activation function, sigmoid or tan H or RLU, right. That is what encoder does. And neural network, the neural network component that reverses this encoding function is called a decoder. So, encoders compact lower dimensional representation data are kept. So, this compact, after this compact lower dimensional representation of the input data input, which is nothing but x, are kept at latent space. This is kept at it. Now, what decoder will do? Decoder will simply reconstruct this data. So, autoencoders basically learn to denoise data, remove the noise, create new data based on the learned characteristics, whatever decoder, whatever the encoder role is there or activation function is there. And then after this, the decoder maps the encoder H back to the original input x using a different set of weights and biases. So, this is the latent space, after that this is the latent space, right. That is what we are discussing, this is the latent space, and then decoder, what it will do? It will also reconstruct this data. Decoder goal is to replicate this data or map the encoding edge, map means reconstruction, this will map this encoding edge back to the original input x. Again with different kinds of this. So, we can write down f prime, let us not write f, let us write g w I g, different w, right. So, we have to write down w I g into x I plus b I p g, and this is the function which will be produced after that. So, that is what it is done. Then obviously, after doing all this you have to find out loss function also, and loss function will measure the difference between the input function and the reconstructions, loss function. Okay. So, at the end you also measure loss function, which will take difference between this decoder and encoded data and do that. That is basically the purpose of this whole whole auto encoder. That is what it is done. Basically, it is a clever technique which allows you to do this encoding decoding as a part of the whole business, so that one can use large images or large data and do that. So, there are different types of autoencoders. First one we talk about is sparse autoencoder. It has sparsity penalty on the coding layer as a part of training requirement. What is it? Okay, it may have more hidden units than the inputs, but only small number of hidden units are permitted to be active at the same time. That is why it is called sparse model. So, it can have many hidden units, hidden layers, that is what is the thing, but at any time only a small number of hidden units are active. Very simple, you can activate small number of hidden units by using a particular time, and that will give you options of it will imbibe the partial penalty. That is what it is imbibe the partial penalty only, and that is very important because they are widely used of applications like image processing or other things. The model is obligated to respond to the unique statistical features of the training data following these constants. That is what it does, but it has many other important features other than this, which probably more important. So, you have an input layer, you see here, that is take care of the input data here, and then you have hidden layers, and you can see at a time 1, 2, 3, 4 active units are there, other are inactive, other 5 are inactive, and finally it gives you this output layer. That is the sparse encoder does. Why it is so? Why you can allow sparsity penalty? Because it reduces the computational time and the computational power also. Next type of the autoencoder is denoising autoencoders. It is a variant of the basic autoencoder, as it attempts to improve representations by altering the reconstruction criterion, and therefore reduce the risk of learning the identity functions. But in a layman point of view, it receives a corrupted data as an input and the train to recover the original undistorted input as output. How does it do? It minimizes the average reconstruction error, and that is why they are used as very powerful filters that can be utilized for automatic preprocessing of data. This is very important, because if you want to remove all the unwanted data, noisy data, it is also can be used for images, image processing also. Whenever you are receiving some image processing thing, some signals may not be so good, they are called noisy data, you can remove it. It can be also used in X-ray diffraction or any kind of diffraction information also. We will talk about it when discuss material informatics. So, ideally speaking, it is a with different variant, but it gives you lot of variety in terms of that. In other words, it receives basically a corrupted data, and a denoising anti-encoder, for example, could be an automatically preprocess an image, thereby boosting the quality and power recognition and accuracy. That is what it is can be done. So, you can actually take a image, automatically preprocess that image using all the noise is removed, and finally improve the quality. The third one is called contractive autoencoder or CAE. Basic idea is to make the encoder robust or small changes in the training data sets. If you have a very small change in training data sets, the encoders must be robust to change of that. The objective functions of any this contractive autoencoder includes an expletive regularizer, and that will force the model to learn onto a training input, learn and also and actually this is and to training input is reduced. So, that means encoding that is robust to small changes in input values. As a result, the learned representations has very large sensitivity. That is what it is. So, in a nutshell, the idea behind these encoders is basically it is proposed by Ruffney et al. In recently 2008 or sometime, is to make their autoencoders robust to small changes. That is what it is. So, DA encourages robustness of reconstructions as we have discussed already, and this encourages robust representation of the data. The last one is called variational autoencoders. It has a fundamentally unique property that distinguishes it from any classical encoder is that it makes so effective for unsupervised modeling. What it does? It maps the input into a latent vector and also the input data in parameters of a probability distribution functions. That is what is the key thing, such as mean or variance of a Gaussian distributions. So, that is why it is called variational autoencoders, because it will map the data or input data into a distribution functions, and so that you can get mean and variance of the Gaussian, it is a Gaussian or Chi or whatever distributions, many distributions possible. So, basically it is nothing new, this probability distribution function. We have seen also in machine learning what kind of different probability distribution functions can be used to that. So, these are the 4 different types of autoencoders. First one is a sparse, where you use very less number of hidden layers compared to the all. Then you have a denoising, it will remove all the noise, basically use a kind of a altering deconstruction criterion. Okay, that is what it is done, and it removes all the noise or something from the data. So, it is a very powerful filter, it can be used. And then you have a contractive autoencoders which can actually use an explicit regularizer, so that the data can be robust or analysis can be robust to any small change in the input data. And last one is the variational, that is what is called probability distributions. So, in a nutshell, neural network that runs how to compress decompose data is called a autoencoder. They are trained to reconstruct the input data from a compressed representations. They aim to map input data to a lower dimensional representation followed by a reconstruction using a decoder, and they are feed forward neural network with encoder and decoder. As well as now the last one is you can used for image reconstructions or image compression, dimensional reductions of any kind of problem which you use in PCA, pairs coordination matrix. The next technique which we will talk about is generative adversarial network or GAN. It is a basically type of neural network, the architecture for generative modeling to create new possible samples on demand. What is that? Well, let us discuss. It says it composed of 2 important parts. One, a generator G, you see a G here, that creates new data having properties similar to the original data, and you have also a discriminator D, this is shown here, discriminator D, that predicts whether this data are likely to be same as a actual data. Well, many material science problem will require you to generate data, right, because your data may not be very large to apply deep learning. So, you have to generate data. In that case, how do you know if generated data and the actual available data are have similarities? So, there you can use this. So, the generator actually generates or creates new data having properties similar to the original data, and once it is done, then there is a discriminator which will predict whether the generated data has a likelihood of becoming similar to actual data. So, it involves automatically discovering and learning irregularities or patterns in input data. That is what it has to first understand, discover and the pattern of the input data, then only it can create new data or generate new data, right. Otherwise, the new data will be out of the match between what is original data. So, this is required. So, many times you will be using this GAN quite naturally, and I will tell you also that this is a technique which has far reaching consequences in the material science. It is basically a new paradigm for this unsupervised learning, and discriminator and generator neural network maps are always in conflict with each other. Discriminator works to separate the authentic data from the produced data. A generator aims to create data which has similarities with that of the original data. So, discriminator will always try to separate the bad data from the good data, or original authentic data from the other bad data. A generator will generate as much of data possible which is similar as the real data. So, after training, a generator in a GAN learns to produce data that is more realistic or similar to the original data. The image generation, style transfer, data augmentation, image generation. If you want to generate image, style generation, style transfer, not generation, or data augmentation. That is what is required in case of machine learning using small amount of data in material science. They all benefit from the GAN, they all benefit from, allows you to do that. Okay? That is the major advantage of GAN. Now, because it generates data, so therefore, the generator is very important. In fact, many of the dark discoveries or NLP also uses GAN. The GAN are essential tools for any unsupervised learning because of the ability to capture the complex data distribution without the need for level input. Though normally unsupervised learning there is no level input, right. You have input data, but there is no level data, but still it can understand the pattern or regularities of this input data and generate similar type of data. That is very unique for this kind of models or this kind of GAN kind of systems. So, GANs are essential tools for any unsupervised learning because it can capture the complex data distribution without any need of level input, but they will require complex training because they can be vulnerable to mode collapse in which generator concentrates on a small number of data patterns. This is called a mode collapse, which is very widely observed in GAN networks, and then it can be only concentrated on the small amount of data patterns. It can completely change the field of machine learning and a significant influence on artistic and scientific domains. And I am telling you, it has significant influence on the material science, machine learning or deep learning, where your available data are very small, then only you can generate this kind of data. The last technique which we will talk about is cone and map or self organizing maps. Okay, this is a technique for creating a low dimensional representation of a high dimensional data while maintaining the topological structure of the data. Remember that we have a high dimensional data, we want to present it in a low dimensional form without compromising on the topology of the structure of data. Topology, you understand, right? The distribution of data, how they are connected, and this is basically a dimension reduction algorithm, and that is commonly used in clustering. Remember this. And what it does, it adopts the technological form of data set by repeatedly moving its neuron closer to data points, allowing us to visualize the enormous data sets and find probable clusters. Remember this, it is repeatedly moving its neurons as close to the data point as possible. By that, it allows us to visualize the enormous data sets and also find probable clusters. That is what it is. Remember, in clustering we find out in different way, but here it is much more generic because it repeatedly moves the neurons to the closer data points and thereby allow to visualize enormous data sets and to find probable clusters. SOMs employ very competitive learning which uses neighborhood functions to retain the input space topological features. It always do that, it always use neighborhood functions. And I will also tell you that basically it is a very intriguing class of unsupervised learning technique. It works very well for any comprehensive and very complex problems, and while it can actually reduce the dimensionality without changing any kind of topological lineage. I hope you understand topological lineage when you talked about the recent tree structure. We have a topology, right, how the tree is developed. So, this kind of tree structures, large numbers of data points can be reduced to a smaller dimensions without altering the T structure, without altering the structure of the T, okay, or structure of these recent trees. That is what is very important. So, any SOM starts with a grid of neurons, and each of which presents a particular area of data space. After that, uses process of competitive learning. The neurons adjust the distribution of the input data throughout the training, and neighborhood neurons change their weights in response to similar data points, making them more sensitive to these patterns. Self-organizing characteristic produces a map that places comparable data points in a very close proximity to each other. So, few things, it starts with a grid of neurons first of all, and then each of these neurons represents a particular area of the data sets. Okay, you have used a grid neurons, each of these neurons will take particular area of the data sets, that is what is done. Now, after that what is do? The process of competitive learning happens. What is that? Neuron will adjust the distributions of the input data. It is in a grid, right? Then they will adjust to the distribution of the data. They will understand how the data is distributed, so that they can adjust itself. And then neighboring neurons will change even the weights, because we are using weights and biases for this in response to the small data points. So, finally, they can make these clusters, right, that is what is done. It can be used in various areas like anomaly detections, feature extractions, data clustering, as I told you, and they play a very important role in case of data mining and exploratory analysis, because they make it possible to find hidden structure in intricate databases without having changes of the topology of the data. That is what the very important thing about it. So, therefore, self-organizing maps or SOMs are very powerful unsupervised learning techniques in deep learning, because it can allow you to cluster the data based on this kind of analogy I told you just now, the network of or the cluster of neurons or the grid of neurons, and these neurons can separate themselves based on the cluster of data. So, I believe I have given you in a nutshell these three important techniques: autoencoders, and then GAN, generative adversarial network, as well as coordinate map or a SOM, which is nothing but a self-organizing. That is why it is called self-organizing map. It can develop clusters, right. These three techniques. There are many other techniques which will be discussed further, which may be finding any usefulness in material science, which we will talk about in subsequent lecture. For the lecture number 29, we are going to start about a different topic, and that is this what is called the different dimensions of the data. In material science, you have atomistics, or rather new even subatomistics also, like electrons, and then you can have data which corresponds to crystals, grains, microstructures, and then macrostructures. How we can actually understand that, different length scales, that we will talk about it, and in the process of that we will discuss about few important techniques like DFT, MD simulations to generate data from different kinds of structures, and that is the next 4 or 5 lectures will be dealt with that, and we will come back after that for advanced deep learning networks and show how can you use in a totality these two techniques and solve various kinds of problems in material science. Let us stop here. Let me thank you for your presence. Please do attend the online sessions or live sessions of the TS, so that you can understand how these techniques are utilized. Thank you.